I'll be here all week. No, probably not, actually. So my name is Mike Boylan-Kolchin. I'm a professor in the astronomy department at UT Austin. And I'm going to try to follow up and expand on John's really nice talk and tell you a little bit more about how we look for dark matter, where we might find dark matter, and how we actually do this both on Earth and in space. And so I think John gave a really good overview of some of the techniques we use to study dark matter. But he didn't actually cover one of the techniques I really like, which is called Google. So if you go to Google and ask where is dark matter, there are 70 million results, about 70 million, not exactly. And so this was actually quite promising to me when I was writing this talk. I promise I actually know about dark matter. Unfortunately, the result seemed a little bit off, potentially, because this is what came back. So I'm not sure if this is anti-Canadian bias or what exactly they're thinking there, but well, let me step back actually a little bit, because I think to understand dark matter, we really do need to understand what we mean by normal matter a little bit better. So what I'd say is that normal matter is easy to understand, okay? And this is easy from the point of view of a particle physicist, so maybe that's not easy overall. So particle physicists have this model for understanding the most basic particles in the universe, elementary particles. They can't be broken down into smaller units. And these particles are shown here. There's 6 quarks. Those quarks get bound together into protons and neutrons and some other exotic particles. Those are typically pretty heavy. There's also leptons. The most well-known lepton is the electron. There are others. They're kind of like the electron, or they interact even less than the electron. And there's also force carriers. So the standard model of particle physics explains how particles like these quarks and these electrons interact with one another and form the basic constituents of matter that we know. Okay? And this model has actually been remarkably successful. So you can write down a very simple equation for this. I did it here. You can probably derive it in your spare time. And this equation actually is pretty remarkable in the sense that you can make predictions that are accurate to the 11th decimal place, or even more so. All right, so this is a very well-tested and very well-verified theory. And it works for pretty much everything we know, as John says. You know, grumpy cats, famous astrophysicists, stars, planets, all of these things. Everything that these things are made up of are these elementary particles that are explained by the standard model. Okay. So where does dark matter fit in? What I haven't shown here is anything having to do with gravity. Okay, John talked about 4 forces. This standard model explains 3 forces. So it explains everything except why things fall down, which is a little weird because that's the kind of obvious thing that you see. But why then is dark matter so hard to understand? Why is gravity hard to understand? And the point is that all of these things of our normal daily existence are made up of these elementary particles, of the forces we actually see on Earth today for the most part, okay? But dark matter, there just isn't that much of it around. So if you ask, in this room, where's the dark matter? You know, well, there is dark matter, okay? But the density of it is a 1 with 24 zeros times smaller than the density of normal matter. So if you're actually going out and looking for that dark matter, it's essentially the equivalent of looking for one specific grain of sand, not just on the entire Earth, but on 100,000 Earths. Okay, so it's pretty hard to find this stuff among all the normal matter on Earth. There's just so much more normal matter, we don't expect to see dark matter's effect around us. Okay, great. Well, let's go out to some larger distance. If you go out to a larger distance like the solar system, hey, now we're getting somewhere. This is only a 1 with 12 zeros after it. Hooray! Now this is, you know, this is 1 trillion times more normal matter averaged over the entire solar system than there is dark matter. So for example, when NASA sends probes out to Pluto and things like that, they don't really say, well, have we accounted for that 1 dark matter particle out of the 1 trillion regular particles that are floating around? That's insane. The dark matter contributes nothing to the gravity in our solar system. It's only really when you get out to the scale of galaxies as a whole like where we are in the Milky Way, something like 24,000 light years from the center of the Milky Way, where you get the density of normal matter being equivalent to the density of dark matter. And this is again because dark matter seems to only interact via gravity and this weak nuclear force. Okay, so it's a very long-range thing. It doesn't collapse at all. Okay, dark matter is hard to understand, but we actually need it. So if you go and average on the universe as a whole, not just around the room here where there's basically nothing, or in the solar system, or even in galaxies, if you go and average over the whole universe, you find that there's actually about 5 times as much dark matter as there is normal matter. And again, Occam's razor might say that's an insane thing to say. But there's actually 3 independent lines of evidence that I can talk about here, and more that I can talk about offline if you're interested, that would say this. And to me, the amazing thing is this comes at 3 very different epochs of the universe. So if you just go and you add up all the matter you see around us today that's gravitating, and you ask how much can be accounted for by the stars, the planets, the gas, all of that normal matter, the things that are made up of those elementary particles, you come to this conclusion that you need 5 times more dark matter than you have normal matter. You get exactly the same number if you study the afterglow of the Big Bang. So there's radiation that comes to us that was emitted 370,000 years after the Big Bang. So that's much, much earlier than now, 13.7 billion years after the Big Bang. And you get exactly the same answer. So this is usually really good when you're doing a calculation 2 different ways and you get the same answer. Either you're doing it right or you've made the same mistake and you don't know about it. Now, fortunately, we can do it 3 different ways. And this third way, I think, is the most convincing in some ways, because basically, if there was just normal matter out there at very early times, 3 minutes after the Big Bang, it would be involved in nucleosynthesis. That is, it would be involved in fusing together of hydrogen to helium, and helium maybe to form lithium. Okay? Helium was all formed during the Big Bang here. And we can do these calculations very precisely now, and we see that we need just the same amount of dark matter as we expect from measuring around us today and from this afterglow of the Big Bang. So this is 3 different ways to measure: 3 minutes after the Big Bang, 370,000 years after the Big Bang, and 13.7 billion years after the Big Bang, all pointing towards the existence of dark matter with the same quantity at every time. Pretty remarkable. And the important thing here, I think, or an important thing, is that dark matter isn't just this hidden normal matter. So one can look for these microlensing events to show that. But again, if it was normal matter, it would participate in this synthesis of the elements 3 minutes after the Big Bang. So even if you wanted to say, well, maybe we're missing things in this microlensing, you can't get away with it at this 3 minutes after the Big Bang era. Okay? So there are many different independent lines of evidence that argue that we need this matter that basically only interacts gravitationally. Another way that dark matter has really helped us out is it has actually provided the gravity in which galaxies end up forming. So in our current theories, without dark matter, we actually wouldn't have been able to form the Milky Way by now. So I'd say that's pretty good. I think this is all pretty sort of standard and accepted science at this point. Dark matter actually gets some less standard and I would say less accepted science as well. From actually reputable places. So this is in Scientific American about a year ago. Fact or fiction, dark matter killed the dinosaurs. I think usually when there's fact or fiction, it's usually fiction, but this kind of read to me like, you know, the guy on the local news who says, astronomers say you need dark matter, but what aren't they telling you? What you don't know could kill you. No, dark matter will not kill you, I promise, and it probably didn't kill the dinosaurs, so don't blame us for the fact that you don't have a pet T-Rex or work on a brontosaurus or whatever like Fred Flintstone. All right, so what actually is dark matter? We heard from John that the leading candidate are these weakly interacting massive particles, so these WIMPs. Let's give some properties of a typical WIMP. So a typical WIMP would be something like 100 times as massive as a proton. So it's a new fundamental particle of nature. Okay, it can't be broken down into smaller units. And it would weigh about 100 times as much of a proton, but it would interact with normal matter extremely rarely. What do I mean by extremely rarely? Well, I was actually really pleased to see we came up with the same number here. So if you hold out 2 hands, it'll be 20 million. Yeah, So what this means is that every year there's some inordinate number of WIMPs passing through a human, and fewer than 10 will do anything whatsoever. And by anything, I mean barely graze, not even make a difference. There's all kinds of stuff that happens much more often than this. So it's extremely hard to see these things. They don't interact at all. How can we actually go about finding these things directly? Well, I think the obvious answer is move to Toronto. But I don't know if anybody's looked at the weather forecast. It's unseasonably warm there, where it's actually getting above 0 sometimes. So that doesn't sound so great to me. Let's not do that. You can actually try to get a lot of normal matter and just hope for one of these rare interactions. Okay? So if dark matter's interactions are quite rare, what you need to do is just get a lot of regular matter and look for that. So that sounds really stupid to me, but that's actually what people do all the time. They collect the biggest things they actually can, right? And they just wait for a dark matter particle to smack into a regular particle and look for that signature. Of course, as I said, there's all kinds of stuff floating around us. And so if you do this just in your backyard, well, you might run into some problems. The background, what we call a background in astronomy, would be the stuff you don't want to see. The background would be billions of times more important than the actual signal you're looking for, and that's not a good situation to be in. So they've figured out a way to do this. They actually go not to Toronto, but to somewhere like South Dakota, and they go a mile underground. Okay, so this is actually one dark matter experiment. It's called the Large Underground Xenon Experiment in South Dakota, and it's in an old abandoned gold mine. So, you know, it's pretty lonely, but on the other hand, you do get to look like you're auditioning for an intergalactic video, so that'd be pretty cool. So what do you actually do here? So what they do is they actually just find pretty much a ton of inert noble gases in liquefied form. So this is actually a xenon experiment. And when I say pretty much a ton, I mean literally they actually go and find a ton of xenon. Literally, 2,000 pounds. This is crazy. They must have some kind of like xenon dealer or something. So if you're looking to sell xenon, these are the guys probably who would be the ones buying it. So what they don't want is things that would interact. So xenon's very inert, okay? But there are radioactive isotopes in xenon which would cause problems in their experiment. And they occur naturally at something like 1 part in a million, which sounds pretty good. And then I talked to these people and they said, well, we really need 1 part in a trillion. So they need to go from 1 in 10 to the 6 to 1 in 10 to the 12. And they have all kinds of fancy ways of doing that. Pretty amazing. So they sit there and they just wait. They're shielded by the Earth, so all the normal stuff that's raining down gets absorbed by the Earth, and then they can look for a signal of dark matter hitting one of these xenon atoms. You would have heard about it if they had seen it. So far, not so good. Okay. There are people who are more proactive in the particle physics community. They say, I'm not going to sit around and wait for dark matter to come and hit me. I'm going to go hit stuff together and make my own dark matter. So this is a dark matter machine in some sense. This is the Large Hadron Collider in Switzerland. It's an enormous ring that accelerates particles to huge speeds, very, very close to the speed of light. They smash together. Okay, normally when they smash together, they just produce other normal particles, which excites them also. But what some of us want to look for is dark matter there. So the idea is every once in a while, smashing together 2 normal particles will actually produce 2 dark matter particles. And again, they're sifting through enormous reams of data looking for signatures of events like this, and you would have heard about it if they had seen it, okay? So they're sitting back waiting for the Nobel Prize to roll in. It hasn't rolled in yet. So astrophysics to the rescue, naturally. Let's go out and look nearby. Okay, so this is our cosmic backyard. We live in what's called a local group of galaxies. Our nearest large neighbor is the Andromeda Galaxy, but there are a bunch of these small galaxies that live around us, and John talked a little bit about them. Let me show you an image here of one of them. This is the Fornax Dwarf Galaxy. It's basically just a ball of stars, okay? So it doesn't rotate like the Milky Way does. It's supported by random motions of the stars. They just zip around, okay? And it's 1,000 times fainter than the Milky Way, so this is a pretty puny thing. But it's not the edge of where galaxies form. There's actually something here called the Draco Dwarf Galaxy that John's done a lot of work on. And it's even fainter, 100,000 times fainter than the Milky Way. And it might be kind of hard to actually see there's a galaxy there, but I think if you squint, you might be able to convince yourself that there's a bit more stars on the right side of that image than on the left. And that's actually confirmed by me drawing a circle there and saying, "Trust me, I'm a doctor." Now, it's confirmed other ways as well, but let's trust me, I'm a doctor. So there's a galaxy there. And you measure this galaxy the same way John talked about, by the motions of the stars being much, much larger than you would expect just from the light you see there. Okay, this is pretty puny, 100,000 times fainter than the Milky Way. What about this thing? This is an image of the Sagittarius One Galaxy, 100 million times fainter than the Milky Way. All right, I can see that a few of you are thinking that dark matter has interacted with me a few times too many. I've kind of lost it. And this isn't going to help. So if I subtract off all of the things in the foreground and in the background, this is the galaxy. Beautiful image, beautiful. So, there are actually just a handful of stars here. You could actually probably name them and try to measure them that way. But again, if you go out and you measure the velocities of the individual stars there, you can predict how fast they should be moving just by Newton's laws, just from the mass there. And they'd be moving pretty slowly, something like 80 meters per second. And when you actually go out and measure how fast they're moving, you see it's much, much different, something like 5 kilometers a second. Okay, so these things are moving 60 times faster than they should be if the mass is accounted for by the light. So either this is an exploding galaxy, and we found a bunch of them like this, which would be quite surprising if they're all exploding galaxies, or there's a lot of mass there that's not accounted for by any of the light in this thing. One really cool thing about these galaxies, so for example, this Sagittarius One has something like 4,000 times as much dark matter in the center as it has normal matter. Remember, here on Earth, we have 10 to the 24 times as much normal matter as we have dark matter, so this is a lot different situation. You can get kind of a reverse particle collider. So you can actually have two dark matter particles smash into each other, and every once in a while, they'll produce normal matter. Okay, so people actually look for signatures of this WIMP dark matter this way. This is called dark matter annihilation. Sounds a bit apocalyptic, but there it is. And so you can sort of point your telescope in space and look for faint light coming from where you shouldn't expect it around these galaxies. Again, we haven't seen it so far. The only evidence we have for the nature of dark matter and the particle nature of it is through its gravity at this point. But there's a lot of hope that either on Earth, as I described before, or in space like this, we might be able to see the actual results of these particle-particle collisions. Another really cool thing about these very dark matter-dominated systems is that if you believe Newton's laws, and we all do, I think, for the most part, then you can go back and say, how would this galaxy actually form? Or how would the dark matter around this form? And this is a question for a numerical experiment. You basically set up a whole bunch of particles, you run Newton's laws a lot of times, and you ask, what do things look like? And that'll give you the ability to see what the universe would look like if you could actually see the dark matter. If you could see dark matter, this is what the Milky Way would look like, right? And the Milky Way, actually, the galaxy itself would be just at the very, very center of that sort of whited out spot. The Milky Way would be surrounded by this enormous gravitational potential of dark matter, a huge number of lumps just floating around it. And remember, I mentioned that there are a few of these known satellite galaxies around. Well, those are what we think are associated with some of these big lumps in the Milky Way. And before 2004, this was kind of a problem. There was something like 12 known satellite galaxies. And you look at this picture and you're like, well, I'm no math whiz, but there are more than 12 lumps in this photo. But telescopes are getting more and more sensitive. So in the decade between, say, 2004 and 2014 or so, there were several more discovered. And just in the past year, there's been an explosion of discoveries of these things. So more and more accurate observations of the universe are revealing more and more of these dark matter-dominated systems, telling us more and more about these particles. Actually, counting these things, counting is like the most basic thing we can do, but this is really a fundamental constraint on the dark matter models themselves. because dark matter doesn't actually have to be a WIMP. Particle physicists are infinitely clever at saying, you've ruled out my model, here's a different model that you definitely can't rule out now. So WIMP dark matter is sort of the favored one. That's what the universe, or the Milky Way, would look like in dark matter if dark matter is this WIMP. But you could postulate another particle, a new fundamental particle that's not a WIMP. It'd be much lighter than a WIMP, maybe something called a sterile neutrino. And if it's much lighter than a WIMP, then it would actually be able to move much faster. Okay. And if that's the case, then it would get spread out much more. And you can see, I think the most obvious thing there is that there are many, many fewer lumps in the picture on the right than the one on the left. So actually, just by going out and counting the collections of dark matter lumps we see around us, as traced by the satellite galaxies, we can actually say we can rule out certain models like this. So that makes some particle physicists happy, some particle physicists really sad because it's their model that got ruled out. But I think it's really remarkable that we're really testing the fundamental particles of nature by looking at the biggest astrophysical scales. And one thing we're going to be able to do much better when we have the giant Magellan telescope, which is an enormous new project that the University of Texas is involved in, is to really measure velocities of individual stars to much, much fainter stars. And that will really help us tracing out these gravitational potentials of dark matter. And you may not think this looks like an enormous telescope, but I'll say that for scale, sort of at the bottom of the image of the telescope, there's supposed to be two people there. So this is a 27-meter diameter telescope. This is large, okay? And they're not joking with giant Magellan telescope. Okay, so just to finish up, the other thing we can do is not just simulate one individual galaxy in dark matter, but we can try to simulate the entire universe and just say, what does the universe look like in dark matter? And this is just a problem that's you can do to as accurately as you can get computer time. So if you're dishing out computer time, please, I'll make more pretty movies if you give me more time. And what you can see is flying through the universe of dark matter, there's lumps pretty much everywhere. Okay? And this is actually really useful for detecting dark matter because we heard a little bit earlier, light reacts to matter. And it reacts to matter in the sense that it reacts to gravity. Okay, so it may not care that there's actually regular matter or dark matter. All it knows is that it should get bent a little bit by the actual presence of lumps along the line of sight. So if you can go out in the universe and look at some very, very distant galaxies, you can actually measure how the light from those galaxies gets distorted as it passes through dark matter and normal structure along the line of sight to us. And this is called weak gravitational lensing. So you don't actually produce multiple images, you just get very small deflections from multiple little dark matter lumps along the line of sight. And what this does is it takes the images of galaxies that you would see if there was no matter in between us. So this is what galaxies might look like really far away if they were purple dots, I guess. And it distorts them. Okay. So you can go back and forth between these, and you can see that the amount of distortion that you get should be proportional to the amount of dark matter along the line of sight. So measuring the shapes of these galaxies and the actual amount of distortion should really tell us a lot about dark matter. And there are many programs that are gearing up to do this in great detail, and their results should be out within the next decade. So I think this is actually quite exciting. So I think hopefully what I've convinced you is that dark matter is really cool. It didn't kill the dinosaurs, we think, but it's pretty amazing that by studying the sort of smallest galaxies we know and the largest scale structures in the universe, we're actually saying something about the smallest particles and maybe some really new fundamental part of nature. So thank you.
All right, thank you very much. So I was reading one of your papers yesterday and you cited me.
Why would you do that? Oh, yeah, fair enough. Yeah.
So thank you very much. We like you. Any questions for Director of Dark Matters in the yellow jacket at the back?
So the question is, I mentioned neutrinos. Are they considered dark matter or normal matter? And so there are three, as far as we know, neutrinos that are part of normal matter. And they do interact very, very rarely. Okay, but we actually know that they can't be what the dark matter is. They just are too light they move too fast, and so they wouldn't make these kind of clumps that we see. And actually, it's pretty amazing. The best way to measure the mass of those neutrinos is by measuring the mass of large-scale structure. So there are 3 standard model neutrinos that are normal matter, but there may be other neutrinos that would be different, and those could be dark matter. And so people are thinking about models like that.
Okay, in the middle here.
About the distribution of dark matter, it seems that the dark matter gleam here is the seed crystal for creating the galaxy. We can't explain the evolution of the galaxy to the galaxy. So, is the dark matter not associated with galaxies?
So the question was, it looks like dark matter basically provides the scaffolding on which galaxies form. Is there dark matter that's not associated with galaxies? And the answer is yes. So dark matter should be pretty much everywhere. It may be very low density, but normal matter really collects up quite well. So it interacts via electromagnetic force, and that's how it cools off and collects into the center of these dark matter potential wells. So as you go in between galaxies, the typical distance between a large galaxy might be, a few million light years. There's still dark matter in between them, even when there's no normal matter there, certainly.
But it isn't gravitationally attracted to itself.
So the dark matter there is just very diffuse, so it does get gravitationally attracted to other things, but maybe there's 2 things pulling on it, and so it doesn't really fall one way or the other so much. It just has many different forces, and it kind of gets balanced out there.
Okay, down here.
So from a dark matter, you say millions of times there are atoms, but what's the velocity and the magnitude of dark, and why doesn't it cause a collision?
Right, so the question is, I claim there's 10 million dark matter particles passing through a hand right now. What's the typical velocity, not just the number, and why aren't they actually causing collisions? So the velocity has a distribution. So the speed of particles in this room is set by a distribution function. Okay, but the typical velocity might be 220 kilometers per second. That's pretty fast. And so it might go up all the way to 600 kilometers a second, or as low as a few kilometers a second. Now, the reason it doesn't interact with us is that actually nuclei are very, very small, okay? And so what you have to have is some kind of effective area to hit off of. And each different force, the strong nuclear force, the weak nuclear force, gravitational force, electromagnetic force, they all have different effective sizes. And the force that these things have, the effective size is just extremely, extremely small. And so they just never actually see anything. So you've seen these kind of models of nuclei, right, that have electrons whizzing around. Well, if you actually made those models to scale, you'd have something that's like a marble at the center and the electron's a kilometer away, okay? So things are very hard to hit. There's a huge amount of empty space in these atoms, and the dark matter just passes through those.
Okay, we've got time for one more question, so I'm going to go towards the back here. I saw the guy with the beard, but you decide.
That doesn't narrow it down here.
Why does dark matter clump?
That's an excellent question. So the question is, why does dark matter actually clump? So it can exchange energy overall with different dark matter particles or lose energy through electromagnetic radiation. But what it can do is convert kinetic energy into gravitational potential energy. So this is normally what we do, with all kinds of things. You just conserve energy, and so the thing will be sitting at very low velocity, okay? And if there's a very slight gravitational potential well that things can fall into, they gain kinetic energy, okay? And then the potential gets deeper, and that's how they're trading it off. So they're not losing or gaining energy, but they're just trading between gravitational potential energy and kinetic energy. And so this is the way they do things, and this is why they don't actually collapse down to some very small scale. There's only a limited amount of ways you can trade that energy back and forth, okay? And so that sets why it clumps and why it clumps down to only a specific scale. But that's an excellent question.
All right, let's thank the director of Dark Matter again. Thank you very much.